Okay, we get to do fundamental theorem of calculus, but I just want to be silly. I want to point out that this is actually really obvious and you actually already understand it. So I'm going to call it the fundamental theorem of money. How's that? And then I'll do a couple other funny things. Well, hopefully you find them funny. Okay, so if you have a bank account, the amount of money in your bank account is your starting amount plus all the changes. And in a bank account, this is either called a withdrawal or a deposit. Okay, if you understand that, then you already understand the fundamental theorem of calculus. So let me explain this. Let me give you some examples. Okay, so when I first went to college, I think my parents made sure I had a certain amount in my bank account. I don't remember what the amount was, but let's say they just give me $2,000. And then over the course of a couple months, maybe my mom said, okay, I think you need more money. So she deposited some more. Or maybe I earned some money. I worked a little bit on campus. So altogether, maybe I got 1,000 new deposits, $1,000 worth of new deposits, but I had to spend some money. So maybe I was living in the dorm and I didn't have any expenses, but every now and again I'd go out to eat or I needed some new clothes or shampoo or whatever. So maybe I spent $500. What would be my current balance or your current balance in that situation? Well, you would simply do 2,000 plus 1,000 minus 500, which would be, in this case, if I did this right, 2,500. So all you did is you took away the money that was spent and you added the new deposits, and that seems obvious. But from a calculus standpoint, the way you want to see this is you want to see your starting balance and your ending balance as being part of this function, which is just your running balances. Okay, so it may look like this kind of thing. And you want to see these guys as your differences, which you're going to see as this sort of thing. So maybe you have 1,000 here and negative 500 here. This is a discrete form of calculus. It's very simplistic, and I hope it seems really trivial to you. But that's all we're doing in calculus. That's what the fundamental theorem is saying. In one case, we're keeping accumulated change, that's your bank balance. And the other function is keeping track of all the little changes that are happening, and that's your little f function. Okay, maybe you say that seems too easy. Well, that's really all it is, but let's do another one. Swimming pools. Swimming pools? Why swimming pools? Well, I want you to imagine that you have a swimming pool and you're filling it with water, and you have a certain amount of water going in. And the reason why this is an advanced, like more advanced than the money explanation, is that we can pour money in at a certain rate. Instead of saying I'm giving you $1,000, I'm going to actually give you a certain amount of water per time. And that makes more sense in the context of filling up a swimming pool. So let's make up a problem. Okay, so start with 1,000 gallons in the pool. I really don't know if this is realistic, so I apologize, but I'm imagining I have a hose that might be able to spit out 10 gallons per minute. Maybe this is a personal pool, a small poolish, and maybe I'm just filling it with my hose. So maybe I can add 10 gallons per minute for an hour. So how many, I didn't mean to say hours, how many gallons after 1 hour? In this case, what you want to do is you want to say, okay, my starting value, so my capital F at 0 is going to be 1,000. And my little f is actually a function, and it's just a constant function, 10 gallons per minute. So actually per hour, it's going to be a lot more. So it's going to be 60 minutes. So it's going to be 600 gallons. So I'm going to add 600, and then f at 1 is 1,600. So it's the same as the bank account example, except that instead of reporting your change as individual changes, you're saying, okay, there's a function that varies over time, or maybe doesn't vary over time, and it tells you the rate at which we're adding or subtracting something, and we have to accumulate that change somehow. Okay, what about the next example? Okay, so let's change the problem. We're still going to start with 1,000 gallons, but this little f over here is the change function, and capital F of 0 is 1,000. So we start with already 1,000 gallons in the pool at time equals 0, and then we're going to add at the rate of 12 minus t over 10. So for whatever reason, the hose is spitting out water, but for whatever reason, it's slowly losing its ability to give us water. And so by the time 120 minutes is up, it's not giving us anything. So how much is this area under the curve? This area is our accumulated change, just like it was, but now we have to figure this out. So how much have we accumulated over that time period? Okay, you did this on the last worksheet, so you should know that it's 1440 over 2, because it would be half of this rectangle if we could turn that into a rectangle. So that would be 720. So I have F at 2 is going to be 1,000 plus the accumulated change, which is 720, which gives us 1,720 gallons in this little pool. Okay, so this is the relationship, but looking at this change function and the change that's being accumulated, and you're going to figure out from this change function what our capital F function is, which is the accumulation of all those changes. Okay, this was the simplest chicken I could draw. I looked this up on the internet, so this is not my original design, but I did draw this. I want to do the fundamental theorem of chickens. Okay, of course this is going to be discrete, but I'm going to start with a certain number of chickens, and then I'm going to have a function that tells me how I'm adding and subtracting my chickens, and then I'm going to know how many chickens I have when I'm done, right? Okay, so let's say we start with 10 chickens on day 0. Each day you increase the number of chickens by the square of whatever that day is. So on day 1 you add 1 chicken, and on day 2 you add 4 new chickens, etc. So how many chickens do you have on day 6 after you receive your 36 new chickens? Okay, assuming my addition is correct, so capital F of 0 is 10. That's how many chickens you start with on day 10. And then little f is telling you all the changes. F of 1 is 1, F of 2 is 4, F of 3 is 9, etc. And so you add up all those changes, and then capital F of 6 has to be 101 chickens. Okay? Okay, and we could have the fundamental theorem of driving a car. Here's your car. I like drawing VW bugs. So you're driving along, and if you know where your first mile marker is, maybe you're at mile marker 4, and then you're driving 60 miles per hour, and then an hour later you should be at mile marker 64, right? That would be the fundamental theorem of driving a car. So this capital F is telling you where you are on the road. That's your accumulated change, and that 60 miles per hour is F of t is 60. Okay, so it's telling you what your rate of accumulating change is, and then all you have to do is integrate from t equals, in this case, 0 to 60, and you're going to accumulate, you're going to accumulate change, but you have to start with 4 because that's where you started, and then you're going to just do 60 miles per hour. I guess since it's per hour, we're just going to go to 1 and dt, and then this is going to be 64. Okay, so how do we figure this out? Like, we can't always figure this out geometrically, so we have a special rule that we now need to explain. So if you didn't figure this out already, the derivative of capital F is little f. So what we're saying is, if you look at your bank account and you're just looking at the running balance, the derivative of that running balance is that change, that list of changes. So they are one and the same. And if you think about this for any discrete problem, like the chickens or the dollar bills, the money, that all should make sense to you intuitively. It just takes a little bit of thinking a little bit beyond that to understand why it's also true in the continuous case. But first focus on why it's true for the money. So if you're looking at the money problem we might represent like this. You started with $2,000 in the bank, and then you spent $500, and then you got $1,000 more. So if you look at these changes, what is the change? It is minus 500. That's you spent 500, and you added 1,000. Okay? So what is this? This is your change list. This is F. This is your little f. That is your list of deposits and withdrawals. So that is your changes or your derivative. But when you're talking about something continuous, it's just that the units are different. Instead of giving the units, when you're doing something that's discrete, here, like all these units and these units are the same. But because we're doing something that's continuous, when we're doing something that's continuous, this isn't just like dollars. You would instead use dollars per minute or dollars per day or something like that. So that's why the swimming pool example explains why a little bit better. So in this case, if your pool started out with 1,000 gallons and 1 hour later it has 1,600 gallons, there's a lot of different ways this could have happened, but the total area under your F curve has to be, whatever this is, has to be 600, because you're going to be giving this in terms of like gallons per minute. And then you're going to have minutes on this axis. You're going to go up to 60 minutes, and then you're going to add all that volume into the pool. Okay? Here's a cute picture from Wikipedia. They're using capital A the way I'm using capital F, except of course they're starting down here at the bottom where the area at the start is 0. And what's happening is this red piece, this red rectangle is sliding to the right. As it slides to the right, the area is getting accumulated. And what they're saying here is this rectangle that we're adding has a width of h, and we're going to assume that the height is roughly the height at the left or the right. It doesn't matter, but just because it makes it easier. So the rectangle is so narrow that we're able to kind of forget this little triangle. And that's actually true. And we've been doing that with the Riemann squares. And so it's explaining why f has to be the derivative, little f has to be the derivative of capital A, or R capital F. Because if you look at this diagram and shove this into the definition of the derivative, then out comes, because you're going to divide by h, out comes little f. That has to be the change function. Okay? Okay, so here's a small diagram that's supposed to remind you of the one you were just looking at. So if f of x is going to be the accumulation, let's just say for the sake of argument, it could be 0 to x of f of t dt, because mathematicians don't like to use the same variable that's changing versus, so this whole thing is the t-axis, but I'm going to call this x right here because, again, mathematicians don't like to reuse variable names like that. So this is f of t, and it's at a specific point x, and capital F of x is all the area that's accumulated up to that x. So capital F of x plus h is the same as the previous f of x plus this little piece here that we just got because of this red triangle. So what is the derivative of this guy? It's the limit as h goes to 0, h goes to 0 of f of x plus h. Why am I having so much trouble writing today? Minus f of x over h. But you see, f of x plus h has got the f of x in it, so that cancels out. So it's going to be limit as h goes to 0 of h times f of x, all right, and the h is going to be down there. They cancel, and so f prime has to equal to little f, okay? And that's the fundamental theorem of calculus. And so hopefully this makes some sense to you. It should just be intuitive. If you're saying this is really just obvious, why is she wasting her time saying this, then that's good. I want you to think I'm wasting your time in a sense, because I want you to think this is so obvious that it shouldn't need to be said. On the other hand, if you are confused, I want you to let me know, because this is really cool, and this is what links together differentiation and integration. Okay, so up until this point, we've only been able to do these integrals if we have a picture. So like if we had x squared minus 4 as a x squared minus 4 kind of looks like this, and then we want to integrate it from 3 to 7 and get that area under the curve. We've only been able to do it if we have triangles, rectangles, and circles to deal with. But now we're going to right now throw in all the polynomials. Let's just say that, okay? And then we'll add in more. But first of all, let's throw in all the polynomials. So the point is, if this guy is little f, the question is, can we find a capital F that goes with this little f? Can we? So we are used to starting with the capital F and going to the little f. I want you to pause the video and think for yourself about what capital F could be that would give us that little f. Go ahead and think about it. Okay, so remember now, our goal is to find f so that f prime equals x squared minus 4. So the answer is not 2x, right? Because 2x is the answer to what happens if we had little f and we took another derivative. We want to go the other way. So we know it's going to be some kind of x cubed, because we know that this is how the powers go. The powers decrease when you're taking the derivative, so it must be x cubed. But if it were just x cubed, then the derivative would be 3x squared. So we're off by a constant. So we're going to have to fudge this by making it 1/3, so that when the 3 and the 1/3 combine, we totally get rid of that constant. Okay? So f has to have that in it. And then because of the 4 piece, well, what do you take the derivative of to give you -4? Well, that one is just a line, any old line with the slope of -4, but that means you could have a 17 or 170, or you could have a pi over here, anything you want, and I'm just going to call it c, anything you want. It's up to you, and that is essentially telling you where your starting point is. This is telling you what mile marker you started at. But for this exercise, we don't actually care, because this question is asking us how far do we travel between 3 and 7. So it doesn't actually matter if you started at mile marker 10 or 100 or 1,000. It makes no difference, because it's just asking you what's the difference between where you were at time equals 3 and time equals 7. We don't actually care where you are on the road. We just want to know the distance you traveled over that time. So since we don't really care, for the sake of argument, in this situation, we just drop this entirely. We just really don't care. And we will care later, but right now we don't care, because we are asking for the total accumulated distance only over that specific time interval. So what we're going to do is we're going to say, okay, if we accumulated, so like capital F of 7, if capital F of 7 were to look like this, and capital F of 3 were to look like this, we could just subtract them, and then we could find the distance that this guy traveled total over that time interval. So let me just calculate that. Okay, and so remember, you are subtracting the -3. So think of it this way. This is saying you started at mile marker -3 and you ended at mile marker 86.33, 3333. So if that's the case, then the total distance traveled is going to be 3 plus 86.333, or 89.3333 is your total distance traveled. And again, it doesn't matter that we dropped this plus c, because we could have made this plus 3 if we'd wanted, and then f of 3 would have been 0. And people do that sort of thing sometimes if we want to just reset everything so that your starting point is 0. A lot of times you do have to adjust that constant of integration to make your problem nicer. Okay? So let me make up another one for you. Okay, so you're driving along the road and your speed is given by this expression. And it looks really complicated, but the point is it's not, because there's a simple function that when you take the derivative, this is what you get. What is it? So this is a guess and check, revise, guess and check, revise, guess and check, revise type of situation. So if this is your little f, you want an f that you can take the derivative of, and it looks like we have a sign in here, but we have the derivative of the sign. So what if we just said sine of x squared? The problem is the derivative would be almost the right thing. It would be sine of x, 2 times sine of x times cosine of x, which is very, very close to what we want. But if we stick a 1/2 in front there, we can get rid of the 2 in the next stage. So we're going to let this guy be our starting function, okay? You might want to pause the video and try it now. Okay, so what you're going to do is you're going to say your total accumulation at pi over 2 minus your total accumulation at 0 is your total distance traveled. So your mile marker at pi over 2 minus your mile marker at 0. So let's see what that is. So this guy, capital F, is your mile marker function. Sine of pi over 2 squared minus 1/2 sine of 0 squared. So what is sine of pi over 2? That would be 1. I did that to make your life easier and my life easier. And sine of 0 is 0, again to make everybody's lives easier. So the answer is just 1/2. You've only traveled a distance of 1/2 because your mile marker at 0 is 0 and your mile marker at pi over 2 is just 1. Okay? Or actually is 1/2. It's 1/2 times 1 squared. I could put the square on the 0 if you like. Okay? So capital F is your mile marker. F is your mile marker. And little f is your speed. Okay? And again, it doesn't matter. You could reset your mile marker. So like if you decided you wanted your mile marker at time is 0 to be 14, that's fine, but it just means that your mile marker at the next at pi over 2 would be 14.5. Okay, so like you don't need to worry about that. You may as well make your life as easy as possible because we're actually looking at the distance between, you know, how far you traveled. So whatever constant of integration you might pick, that capital C, if you want to change that, that's fine with me, but we usually just drop it off in this situation because they're just going to subtract from each other anyway. Okay, I want to talk you through this plowing the streets question on a conceptual level. I'm not going to give you the same numbers as what's on your worksheet, but I want you to understand the model here. So we're making this model that says capital C is the total amount it costs the city, let's say of New York, to remove a certain amount of inches of snow. So let's say, for example, the cost to remove, let's say, 12 inches of snow is like $10,000, let's say. But maybe the cost to remove 6 inches of snow is $3,000. Okay, so what we're saying is meaning for one snowstorm. So the model is saying that, this model that I'm just making up here off the fly, okay, is saying that it's not so hard to remove a little bit of snow, but as it gets worse and worse in the city, those additional layers of snow are harder to get rid of. So maybe if it's just a little bit of snow, they can just plow and shove it up on the side of the road. But then as you get a lot of snow in the city, you actually have to think about where you're going to put it, and you have to drive it further away. It costs more to get rid of the additional snow. So it's not just like, let's remove 6 inches and remove 6 inches more. That's not really how it works in the city. Does that make sense? Hopefully that makes sense. So this is the model we're working with, and we want to know like what is going on here. So if we know that it takes $10,000 to remove 12 inches of snow and only $3,000 to remove 6 inches of snow, then what you're trying to do is you're using this little c. So this is a capital C. It says the total amount to remove that much snow. Little c means the extra money it costs to remove that amount of snow. He used DN in the problem when he wrote it. So this would be saying this is 7,000. The extra money that you need to remove inches 6 through 12. And so this function is going to look something like, kind of like this. It's going to be increasing. The derivative is going to be positive, but the second derivative is also positive because it's getting increasingly harder to remove more snow. Now you might be in a city where it's the opposite. It might be that once you call out more laborers, the incremental cost to remove more snow is less. But maybe you don't live in a tightly packed city where it's hard to find places to put the extra snow. Maybe you're in upstate New York where you have right, left sides of the day, and there's always a place to put the snow because the cars have already moved. You know, so it depends on a lot of things, whether you're going to get this kind of shape or this kind of shape. Okay? But that's the model.